session and the other towards mirror P from W.
Okay, thank you for the introduction. It's nice to be back in Miami and at this conference again. So I want to talk about, I guess, some results and some hopefully future results that I've been thinking about for a long time. So this is joint with Sukjoo Lee. So I'm going to start, I hope, pretty slow, some very, very classical things for the moment. So going back to, I guess, maybe the prehistory of mirror symmetry, the idea is that if you start with a pair of Calabi-Yau, in this case I'll say orbifolds, the first thing you want to check to see whether they're actually a mirror pair, in whatever sense you want to take mirror pair to mean, is to check that their Hodge numbers agree in this sense, right? So the idea, is that the Hodge numbers should satisfy this relation. So D is the dimension of the two Calabi-Yau varieties, and I'm going to look at orbifold cohomology here. It doesn't really matter for the purposes of this talk. You can sort of take that to be usual cohomology. So this is the most basic check you can use to see whether two things actually produce mirrors. It should be a consequence of whichever form of mirror symmetry you're interested in looking at. So maybe the first big result, or one of the first big results in sort of the mirror symmetry literature, is this result of Batyrev-Borisov. So I'll explain it in sort of the Batyrev case, not the full Batyrev-Borisov case, but I think most people know all of this already. Is that if I take a pair of reflexive polytopes, which we'll call delta and delta check, to these polytopes, there are corresponding toric varieties. So these are Gorenstein toric Fano varieties. They always admit a crepant orbifold resolution, though not necessarily a crepant resolution themselves. So if you take these toric varieties and you take anti-canonical hypersurfaces inside of these toric varieties, they satisfy this mirror relation here, right? This is the basic thing. So this was proved by Batyrev and Borisov back in 1996. So this was largely a combinatorial result that built off of work of a number of people, Batyrev himself, along with work of Danilov and Khovansky. It's sort of, but in essence, it's very combinatorial. So throughout the years, there have been a number of other results that have reflected things like this. So for instance, if you take pairs of Calabi-Yau varieties coming from the Gross-Siebert program, they satisfy this topological mirror test. This was something checked by Gross and Siebert. Maybe another example where this is actually satisfied is this construction of Hosono, Lee, Lian, and Yao. So this is a much more recent sort of construction, which maybe I'll spend a little bit of time talking about here. So it's related in spirit to the Batyrev-Borisov construction in the sense that it starts with these toric varieties T delta and T delta check. So attached to two reflexive polytopes delta and delta check, you take a double cover. And this double cover is branched along the anti-canonical hypersurface X delta that I mentioned above. So these are smooth or quasi-smooth anti-canonical hypersurfaces. So it's branched along X delta along with the toric variety, the toric boundary. So the idea of Hosono, Lee, Lian, and Yao is that these two double covers are mirror in some sense. So maybe I'll make a brief comment here. So these are orbifolds because they're the ramification or branch locus is singular. It has normal crossings. But they check in dimension 3 that these two things have Hodge numbers that satisfy the usual duality. And maybe I'll just mention as a little bit of a self-promotion that using the results that I'll mention throughout the rest of the talk, myself and Sukjoo were able to prove this in arbitrary dimension. Okay, so outside of these, I'm not entirely certain how many different cases of Calabi-Yau varieties satisfying this duality there are. I don't know of any other sort of major broad constructions outside of these that actually satisfy this property. Okay, So this is the Claviau case. Mirror symmetry, I guess, as the years have progressed, has been understood to be a phenomenon that occurs for many other different things. So maybe I'll make a couple comments about what this topological mirror test sort of looks like in different cases. So maybe first of all, I'll mention the BHK construction. So this is Berglund-Hubsch and Krawitz. So in the BHK construction, the objects that appear are essentially pairs of orbifold singularities attached to a matrix B. So to a matrix B, I can, so this B will be a square matrix with positive integer entries.
Mirror means nothing.
Here? I will talk about the Hodge theoretic verification in these tables. I'm not going to mention anything beyond, just pure numbers in this talk. So if you start with a square matrix B, you get potential W coming from B and coming from its transpose. Choosing a finite group action, we get a quotient on both sides. So we get C to the D modulo some Q. And then there's going to be some other action here on the dual object modulo some other maybe transpose subgroup, something like this. And so if you want to verify topologically that these two things are mirror, what you do is you compare what are essentially some version of Hodge numbers for the vanishing cycles of these isolated singularities. So I think I didn't say isolated singularities. So this construction gives more than just isolated singularities, but this has been verified largely for the isolated case. So here what you do is you take yes. Yeah, it's some finite group, finite subgroup of the torus. It's finite abelian. It's fairly straightforward. There's some combinatorial construction here. So to verify topologically that these two things are mirror, what you do is you look at the vanishing cycles of sheaf of vanishing cycles. This carries a mixed Hodge structure. It also carries an action by a semi-simple automorphism. You look at the eigenspaces of the semi-simple automorphism, and you take the Hodge-graded pieces of those eigenspaces. I think it's possible that what I wrote down here is actually sort of nonsense, but in spirit, this is roughly what you look at to look at the sort of mirror Hodge theoretic invariance. And so it was checked, in this case, I think by Krawitz, maybe the first person to do this, that there's a similar duality of Hodge numbers, or these variance in Hodge numbers for the BHK mirrors. And so maybe the thing to point out, and this will be something that appears later in this talk, is that, okay, you should take this definition with a grain of salt, but roughly what's going to happen is you're going to have rational indices appearing here. And so that's something that's not true in the general case, or the case of Claviau's, but that's something that appears here. Okay, so these are things that appear from vanishing cycles. Another example where the sort of topological duality has been checked is the Gross-Kitsarkov-Rudat paper. So this is, in this case, they take complete intersection varieties or hypersurfaces of general type that live inside of a toric variety T delta. And the mirror object here is a Landau-Ginzburg model, which I'll write YW. So this is something where the total space is dimension equal to the dimension of the underlying toric variety T delta here, plus the codimension of X. So really what's happening in this case is you take your complete intersection in a toric variety, you take the vector bundle, the total space of the vector bundle from which that complete intersection arises, and the sections of line bundles that define X give you a potential function on the total space of this vector bundle. That gives you a Landau-Ginzburg model. And what you're doing is you're constructing the Landau-Ginzburg mirror to that Landau-Ginzburg model. So that gives you this object here. So the invariants that are compared in this case are actually a bit simpler than in the BHK case. So you compare the usual Hodge numbers of the complete intersection X to the Hodge numbers of the sheaf of vanishing cycles of the dual Landau-Ginzburg model here. So maybe D is a little bit mysterious in this case. I should probably have a shift up or down for this, but it's essentially some variant in this sort of Hodge diamond flipping idea. Okay, so these are two cases where these things have been studied, and maybe the last case, yeah. It's on the central fiber of Y. So yeah, so I can think about this as precisely what's happening here is I have a map from Y to A1, and then the central fiber is some normal crossings object here, something like this. And then I have a sheaf of vanishing cycles living on the central fiber, and I'm looking at the Hodge numbers of that sheaf of vanishing cycles. Okay, so that is kind of an interesting point because this Landau-Ginzburg model is, in general, it might have more singular fibers living off towards infinity. So these aren't being taken into account in the GKR paper. So this is maybe something I'll mention a little bit later. The last example that I'll mention, and so this is, okay, I don't really know. I'm saying GHV to sort of talk about Givental, Fourier, and Vafa, but this is sort of a subset of their, sort of an example of their construction, and the Hodge number duality I'll mention in a little bit. So here maybe we'll start with the toric Fano complete intersection, and what you get out of this is a Landau-Ginzburg model YW, where if you do this correctly, Y is again a complete intersection, and W is some potential function on Y. Okay, so I won't go into detail about this. The construction of this thing, at least in sort of as a hypersurface or complete intersection in the torus, is pretty straightforward and combinatorial. There's a little bit of elaboration necessary to make this work on the level of actual complete intersections. So the Hodge theoretic invariants to take into account in this case, and these are things that I'll talk about a little bit more later, are, so the initial invariants are the, let's say, orbifold Hodge numbers of X. So X might be inside of a toric Fano orbifold or toric orbifold. And the Hodge numbers here are things that come from, well, okay, I wrote this down, I think because you was the first person to define these things completely, but they're also related to invariants that appear in a paper of Katsarkov, Kontsevich, and Pantev. In I think 2017, I think was when it was published. So these are, so maybe just a comment, these aren't the same thing. So they look very similar, or they don't look very similar to the Hodge numbers of the sheaf of vanishing cycles that appear in the previous two cases. And so if you think about, if you actually say what these things are, this is a global Landau-Ginzburg model, so it maps again onto A1. And the Hodge numbers here, these are also, well, okay, it's a bit of a long story, but they take into account more global data. So the Landau-Ginzburg model looks sort of like this, but it's also taking into account stuff that appears nearer to infinity. So it takes into account all the singular fibers that appear in this Landau-Ginzburg model. Okay, so this is more or less, you know, three different contexts where, four different contexts where some variant in this Hodge theoretic mirror symmetry is known. Okay. Okay, so we have all these things, we have all these constructions, they're all very toric, they're all very nice, and we know a little bit about the Hodge numbers. Maybe I'll make one comment just giving some attribution here. So of course, this expression was proved for hypersurfaces by Gross, Katsarkov, and Rudat. The preceding example, there was something proved by Krawitz. I think this case, there wasn't much known until the work that I'm going to talk about today. It's not known in broad generality. I think it was proved for certain complete intersections that some of these Hodge numbers agree by Prushkovsky and Shramov, but it's not very well known. Okay, so we have these Hodge numbers, and so maybe I'll talk about a more general mirror construction. So this is a construction that was, I guess, introduced by Patrick Clarke. I mean, it's a very broad general construction. It's in his PhD thesis from, I think, 2008, or that's when the paper appeared at least. So the idea is to take two different fans, and so I'll be a little bit more broad than Patrick was and talk about stacky fans. So when I say stacky fans, I mean something very naive. I mean, essentially take a fan and I allow scaling of the ray generators of this fan. So you can build a stack from that data, a toric stack from that data. So I'm going to take two different fans in the lattices NR and MR, respectively. And I'll say that these two fans are Clarke dual if this relationship holds. So I mean, it's a very simple relationship. It's just saying that if I pair things in the support of one fan with the other, I get a positive number or a non-negative number. And so the geometric consequence of this, and there's nothing really too complicated about this, is that if I take the potential function W sigma, which is just on the big torus, this is just a Laurent polynomial whose monomials correspond to the ray generators of sigma. This is a regular function on the toric variety attached to the dual fan, this sigma check. So that's all this is saying. So maybe I'll bounce over here for a second and show you an example of this. So here we have something I'll call sigma and sigma check. These are very clearly just two fans sitting inside of dual spaces, if you want to think about it that way. You can check that the relationship I mentioned holds for these, just because one of these lives in the upper in the positive quadrant, and the other one also lives in the positive quadrant. The thing that I want to notice here is that I don't require the support of sigma and sigma check to be dual. There's nothing at all about this. It's just very, very sort of open and broad here. Okay, so going back. What's that? I just want to emphasize the fact that these don't need to have dual support. That's all. It's not a very serious remark. Is that okay?
So what is dual?
Oh, dual would mean that, I mean, if I have a fan, right, I can take the dual cone, right? So these have support, which is cone, which is a pair of cones. I don't want the support to be necessarily the dual cone. It can be contained in the dual cone. Yeah. No, don't want that. Okay, great. So we have toric data coming from these things. And so the basic point to make, and this is what I think the goal of Patrick's work was that this mirror construction subsumes more or less all of the constructions that I mentioned above, right? So the BHK construction, the...
is this a construction? I feel like there are a lot of Clarke dual pairs.
Yes, there's tons of Clarke dual pairs. Yeah.
Like anything that they both live in the positive quadrant.
Yeah.
So how is it a construction?
Sorry, do you have... Yeah. Oh, yeah, sorry. So is that the question? Yeah, so this is... okay. So the pair, yeah, I guess I didn't precisely say that, though it's written here, is so on one side, I have the toric variety coming from sigma with the potential coming from sigma check. And on the other side is the toric variety coming from sigma check and the potential coming from sigma. So maybe I'll show you the rest of my picture here. And this is sort of a tropicalization picture of what happens in this particular example. So some of the data I'll mention a little bit later, but here I have two pictures. So the first, here, what I mean by this is sort of the moment polytope of the toric variety coming from the fan, the first fan here, so sigma. And then if I tropicalize the potential function, I get something that looks like here. So the potential function coming from the second fan gives me this. Okay. And then on the other side, if I tropicalize the toric variety coming from the first fan, maybe I'll zoom out, I get what I've drawn in black here. And if I use the potential function coming from sigma here, right, this should just be sigma, not sigma check, I get the green object that I have here. Right, so I think these types of pictures I think I remember seeing in a paper of Helge Rudat from a long time ago.
We're not claiming that this subsumes by contrast with
No. Oh, I'm so sorry. No, I didn't mean that. No. Of course not. No, I meant that it subsumes all the toric constructions in the previous slide. Yes, apologies. Yeah. No, very far not. Yes. The fan on the right is what? Sorry. Yes. Yeah. Yeah. Sure. I mean, this is just a cartoon, but yes. Oh, what's on the left? It's a blow up of C2 at a point, or a weighted blow up, I guess. Yeah. Other questions about this?
Can you see the formula for potential again?
Yeah. I just want to do that. So it's just the sum of the monomials coming from the rays of the initial fan.
Also seem to have like the original part.
Okay, sure. I can add the origin if you want. Yeah. Thank you. Is that okay? Okay, great. Good. So, right. So I'm going to impose two extra conditions on here. Are you okay?
There's no tropical variable or something, no function, nothing.
No. This will appear later. And this is what I'm talking about now. Yeah. So I'm going to impose two different conditions on this. So okay. What I should first say is that Patrick's construction did not assume anything like that. Very, very broad. I'm going to impose two different conditions that make this less broad. The first is that sigma and sigma check are quasi-projective, which means that I have some affine linear function, some sigma affine linear function that sort of corresponds to an embedding into affine space. I mean, so this tells us this is affine linear data on the fan sigma and sigma check. So that's I think what you mean when you say tropical data, right? And that's
Something tropical.
Exactly, yeah. So in order to do that, you do need this data here. Yeah, exactly. Sorry. Okay. I mean, you could use the same word to talk about the fans as well. So, but yes. And secondly, we want a convexity condition on the polytope on the sigma one and sigma check. Right. So this is true for sigma and sigma check as well. So I want the ray generators to essentially form, along with zero, to form some sort of convex polytope. So just to sort of explain what I mean in terms of these pictures here. What I don't want is something like this. So if I had something like this, a ray generator here and a ray generator here, so that would be bad, because then if I took the convex hull of the origin along with the ray generators, I'd find something in the interior. And so that again, if I think about that in terms of the tropicalization, that would mean that I end up having things that sort of don't come from this fan. So if I'm going to draw this in green, that would correspond to things that look like this, like that. Maybe I'm drawing this poorly. Like that. I would have like connecting points here that don't necessarily come from the cones of the fan. So this is what the convexity condition means. So I want, yeah, so okay. All right. Okay, so I assume these conditions, and then I ask myself, what would a topological version of a mirror test mean in this particular case? And so the answer to this question comes from, I guess, work of Jingda Yu, and so subsequent work of Yu, Saba, Eno. I said that wrong. Eno, Saba, and Yu. And so you look at the twisted cohomology of this Landau-Ginzburg model. So this is the usual Durham complex or Durham sheaves on Y equipped with this twisted differential form. And then U defines a rational filtration on this complex, coming from sort of the poles of this function W. Okay, so here what I'll do is I'll take a compactification x of y. So D is the divisors that I'm adding at infinity. And then I'm going to split. So this function W gives me a rational function on here. So I can look at the order of poles along different components of D. So I'll assume that this is a normal crossings compactification. And P is going to be the polar locus of W, so the components along which I have poles. And then I'll have an auxiliary component E. Okay, so U's filtration is something along these lines, where essentially I take the subcomplex determined by things with log poles along the entire boundary D. And then I have poles of particular possible orders along the polar locus. Okay, so there's something like this. This is defined for all rational numbers, and it induces a filtration on cohomology. It's not entirely obvious just from the definition that this is, well, there's a lot of things that aren't entirely obvious in this just from the definition. But this does, in fact, give you a rationally graded filtration on twisted cohomology. Okay, so the theorem, yes? Yeah. Lambda has to be an integer. Lambda can be rational here, right? So when I say P here, I should be clear and say that this is the full polar divisor. So this has integer coefficients on it, corresponding to the, maybe let's let P be the polar divisor, and let's let this be the support of the polar divisor. Does that help? Yeah, exactly. Yeah. And so when I say this, I should say maybe a few more words about this. This is going to be a rational divisor, lambda P. And when I say take the 4 of this, I mean just take the 4 of the coefficients of that rational divisor. And this object is going to be 0 when I get something greater than 0. Okay. Okay, so the theorem that I proved with Sukjoo in, I guess the preprint came out last year, was that if I have any, actually I should be more careful here, and I should add 2 more words here. So orb. So maybe, okay, one thing I didn't mention was that I do want so these to be simplicial. I want these to be simplicial fans. So okay, so once I have that, I have a well-defined notion of orbifold cohomology on these guys. And so the theorem is that for any rational numbers lambda and mu, I get this usual duality relationship between these the lambda u mu Hodge numbers of this mirror pair. Okay. So I have to assume that both this quasi-projective condition and this convexity condition hold. But as a consequence of this, we're able to reprove the results of Batyrev-Borisov. This proves a conjecture of Katsarkov, Kontsevich, and Pantev, and maybe I should say that with sort of a grain of salt. What precisely this proves is that if you take quasi-Fano complete intersections in toric varieties, there's a dual Landau-Ginzburg model that one sort of constructs using this Givental-Hori-Vafa construction. And you get that the Hodge numbers of the original toric variety or the original complete intersection match the U's Hodge numbers for the Landau-Ginzburg model. So this is, so the conjecture of Kotsarkov, Kontsevich, and Pantev was that if you have homological mirror dual Fano-Landau-Ginzburg pairs, you have this duality. So what we're proving is not, of course, that we have this homological mirror pair. We're proving that this Hodge number duality holds for complete intersection Fanos. And so this also proves and extends this result of Krawitz for BHK pairs that appeared back in the literature maybe a number of years ago. Okay, so this is essentially the construction. Maybe I should make a very brief note. I mean, so I'm not claiming that this recovers the result of Gross-Kotsarkov and Rudat that I mentioned before, because there's some small subtle part of that that's not that doesn't sort of fit into this construction that I mentioned. So the GKR mirror pairs fail to satisfy this convexity condition. So what we actually are able to get, and I guess conveniently drew a picture of this earlier, is that so here what we have something like this. So we have a Landau-Ginzburg model over A1. And then we have a fiber here, so a bad fiber, and a bunch of other singular fibers living away from 0. So this is over 0. This is over some finite number, so A and B. What we're able to prove is that if instead of this, what you take is the HPQ orbifold YW. So just the same objects that appear in this the statement below. So these Hodge numbers give you the cohomology of HPQ of X. This is equal to that, and so I should say D minus P Q. And then I add to this a collection of copies twisted, sort of shifted by some rational number of HP plus maybe alpha, Q plus alpha of the ambient toric variety T delta. Right? So there's some modification of the GKR result that we're able to prove that doesn't actually recover the GKR result. Okay, so that's just a comment on this. So
can you plus one again?
This one, yeah, this plus one.
So like you don't have the plus one for the Berglund-Hubsch.
So I don't have plus one for the Berglund-Hubsch. No, yeah, no, and that's true. But I mean, I'm really only interested in like the relative cohomology with respect to a generic fiber. I mean, yeah, I don't think this plus one is a big point for us. Maybe I can talk to you about it later. Okay. Okay, so maybe, yes. Yeah. Yes. Yeah. Yeah.
That induces filtration on labeled by some rational number.
Yes. Uh-huh.
Then in the theorem downstairs, you have two rational numbers.
Yeah, okay, that's a good point. So there's a second rational number that's I sort of swept under the rug here. So since I'm considering orbifold cohomology, and these aren't necessarily Gorenstein orbifolds, there's a second shift that comes from that. Yeah, exactly. So there's really like two different appearances of rational numbers here coming from both the use filtration and the orbifold cohomology, this conjugacy class, and those two are being shifted exchanged under mirror symmetry. Okay. Okay, so maybe I'll say a few words about the proof of this construction. So the QC-QP condition here basically allows us to build a degeneration of families of Landau-Ginzburg models. So when I write the script T here, what I mean is I build a family of Landau-Ginzburg models living over the disk D, where a generic fiber is one of the Landau-Ginzburg models coming from Clarke's construction. So if I look at the central fiber of this degeneration, the strata of this central fiber, so there's some family of Landau-Ginzburg models, the strata of this central fiber are indexed by this, I guess, fan poset object here. So it's pairs of cones living in sigma and sigma check so that they pair to give 0. So we have objects here. So, okay, so we have these fibers, and then we have a stratification spectral sequence on the nearby cycles sheaf of this twisted cohomology. What we do is we prove that this spectral sequence, the corresponding spectral sequence, degenerates at the E2 term. And so since we have degeneration at the E2 term, you can compute the cohomology or the graded pieces of this cohomology using a sheaf on the polyhedral space S here. So you can then, so this is, I think, the statement that I just made. So there's some filtration K on this nearby cycle sheaf that allows us to compute this. And similarly, if you take the sort of the dual data, you build a degeneration of the dual Landau-Ginzburg model, and you get a second sheaf. And the sheaf lives on exactly the same space. Since, I mean, I guess if you look at this not at all closely, you see that this doesn't depend on tau and tau check. And so you get another sheaf living on the same space that computes the cohomology or the cohomology of the nearby cycles of the twisted cohomology on the dual. You then check that duality holds on stocks to obtain this result. So this sort of approach to proving this type of statement has appeared in several places in the literature. Maybe just to give you a little bit more of a sense of how this works in this case, I wrote down part of an example. So if I think about the tropicalization of these objects here, so as I said, I have tropicalization. And so this might have been a little mysterious when you saw it before. There's a number of cells inside of both of these tropical sort of complexes corresponding to pairs here. So pairs of cones living inside of here and here, that pair to give me 0. That's where this object appears. And so just to look at this, this cell here corresponds to the vertex on both of the fans that I'm looking at. And so similarly, you can go through and check that there's a bunch of these cells that correspond to those. So it's not going to be every single cell that corresponds to such a pair, but there's going to be enough of these cells that the corresponding stars of those cells give me an open cover of the tropical variety. So that it's using that along with the check argument that allows us to compute this cohomology. So, and to maybe give you a brief idea of what the stocks of these sheaves look like, on one hand, you have the stocks of J look like, take the orthogonal complement of the first cone, and then you take the volume form on the second cone, on the linear space spanned by that second cone, and you take the wedge of these two things, and then you tensor by these two beta tau and beta tau check factors. These are factors that come from, they're trivial or they're isomorphic to Z when the underlying cone is unimodular, and they carry data about the orbifold structure on one hand and the irregular filtration on the other hand of a simple Shell polynomial. So this is where like the orbifold data appears. Okay, and so you can kind of see if you do this dually, you just get, there's some linear algebra here to show that those are dual, but that's easy. Okay, so that's roughly what goes on in this proof. Okay, so I mentioned that I would try to talk about mirror P equals W as well. So the idea, okay, so just so maybe I'll start with this statement here. So another consequence of this theorem, and okay, I'll hide that and then I'll get back. So another consequence of this theorem is that if I have two log-Calabi-Yau mirror pairs, so you can either, the construction of Batyrev-Borisov can be extended fairly trivially to give you mirror pairs of log-Calabi-Yau varieties or perspective mirror pairs of log-Calabi-Yau varieties. So you can do this, and a consequence of the work with Sukjoo is that you can show that this type of duality holds for log Calabi-Yau mirror pairs that come from complete intersections. So here I have HPQ on one side and HD minus PQ on the other side, where I mean that HPQ is the dimension of the QF graded piece of HP plus Q on this cohomology. So I just take the Hodge filtration on the cohomology of X minus D, and I compare the Hodge graded pieces of one side to the mirror. And so the question then, I mean, if you know about mirrors, Hodge theory at all, it's what does the weight filtration do under this mirror relation, right? So there's always a canonical weight filtration on the cohomology of a non-compact variety. And the question is, where does it go under mirror symmetry? Okay, so that's the idea. So this is something that I think we've been talking about maybe in lots of places, including this conference in past years, for a long time. So I think this is maybe the first time we have actual results or something resembling actual results in this direction. Okay, so the slogan, as I wrote before, it's that if the topological mirror test is an artifact of mirror symmetry, you should think about mirror P equals W as being an artifact of functoriality in mirror symmetry. So to explain what I mean by this, I'll go through sort of an example, and this is explained really well in generality in a paper of Sukjoo's from 2022. But here's the basic idea. So if I have for instance, Fano variety X and a anti-canonical hypersurface D inside of X, then one expects in a very broad sense that the mirror is going to be a pair consisting of X and a normal crossings boundary divisor D with a proper map over A1. Right? So this is, I guess, fairly general. And so you have a couple functors appearing in both sides of the mirror here. So here you have a functor of the push forward functor coming from the derived category of D to the derived category of X. And on the other side, you have some sort of cut product functor relating the Fukaya category of a smooth fiber of the Landau-Ginzburg model to the Fukaya Saito category of Y and W. So you should take this as very broad inspiration here. I don't think much of this is, I'm not saying it very precisely at all, at the very least. So on the cohomological level, you have a corresponding map. So applying the Hochschild homology to this, you get a push forward in cohomology between the PQ cohomology of D and the PQ cohomology of X. And on the other side, you get a boundary map in the relative cohomology or relative cohomology along exact sequence. The idea then, which is pretty straightforward, is that you can use this map. So this appears in the residue cohomology along exact sequence, maybe relative cohomology exact sequence. And you can see that the co-kernel of this map just gives you the P plus Qth weight graded piece of HP plus Q. And the kernel is just the P plus Qth weight graded piece of the P plus Q minus first cohomology. And so these pieces give you parts of the weight filtration. In fact, if you take all these maps together, that literally just gives you the weight filtration in the cohomology in this case. So in this particular case, weight filtration is very direct and straightforward. There's nothing really complicated going on here. Just because the divisor D is smooth. And on the other side, again, this is a fairly trivial thing. I mean, I mentioned Di Cataldo and Leray here, but it's not really that complicated a result. In this generality, it's that if I take the co-kernel of this map rho, this gives me a piece of the perverse Leray filtration with respect to this map W onto A1. So this is the affinization map of X check minus D check. And the kernel of this map is again another piece of the perverse Leray filtration. Okay, so this is something that's explained in a large, much more generality in this paper of Sukjoo's, but this is the most basic case where this appears. Okay, so this example motivated a conjecture, I guess, of myself, Ludmila and Victor Prushakovsky, which says that if we have two mirror log Calabi-Yau pairs, then we should have this sort of identification of Hodge numbers. So we should have, we take the weight graded pieces on the U side and the perverse Leray graded pieces on the other side. And I should be careful to say, what is this perverse Leray filtration? So you have an affinization map for U check. So I want to take the perverse Leray filtration with respect to this affinization map. So I take this, and then I take the Hodge graded pieces of these two things, and they should agree in general. Okay, so this is a pretty broad, the statement is then that what is mirror to the weight filtration, the perverse Leray filtration of the affinization map should be mirrored. Yes. Yeah. Why is it affinization? So this is something I'm sort of imposing on the situation. So essentially what this should be is the Landau-Ginzburg mirror of X, and W should be the potential function. I mean, why is the map to A1 affinization? So yeah, I'm assuming it's proper. So it's a consequence of that. Yeah. Okay, yeah, this is a good point. I've been thinking about this for years, and I don't know what the relationship between this P equals W conjecture is with the usual P equals W conjecture. I have not been able to find a concrete relationship. From what I can tell, I mean, these are sort of different types of mirror symmetry appearing in both cases. So I'm not sure what it should be. If anyone can tell me what that is, I would love to hear it. Okay, so maybe yeah, okay, yeah, I don't know. Okay, so maybe just as a brief consequence of this, if I just following through the idea, if X minus D is affine, then you can just very easily compute that the perverse Leray filtration is just the degree filtration. This is a consequence of the Lefschetz hyperplane theorem. Then tracing this through, what this says is that the cohomology of the original object is mixed Tate. And this implies that the boundary divisor is maximal. So there's a point at the intersection of different divisors in here. Right, so I think this is something that's sort of well understood to hold in mirror symmetry, and this is a consequence of this conjecture. Okay, maybe. Okay, how much time do I have left? Not that much. Okay, so I'll skip this example and maybe make a comment. So in general, if you take the quantum cohomology of this complement, and the boundary divisor is 0, so in this case, that just means that this X minus D is a Calabi-Yau variety. So if I take the quantum cohomology of a Calabi-Yau variety with the gamma integral structure, this will give me an integral variation of Hodge structure near the large volume limit point. What we expect is that if we take the quantum cohomology of this log Calabi-Yau variety and equip all of this data, so the gamma integral structure, whatever this means, plus quantum connection, if we equip this with the perverse Leray filtration, one would expect to see a mixed Hodge structure on this quantum cohomology. So this is, I think a lot of the words that I've used here are very vague, and I think a lot of this, I don't know how to make it not vague, but this is a general expectation here. Okay, so in the last maybe 10 minutes, I'll spend some time talking about a proof in progress of this mirror P equals W conjecture for Clarke mirror pairs. So there's a couple things one would want to define in order to make this precise. So if I start with the Clarke setup, so if when I started with two log-Calabi-Yau varieties, the weight filtration was clear. That's just the usual Deligne weight filtration. And the perverse Leray filtration is also, if not entirely clear, at least canonical. So it comes from the affinization map. Neither of these two things exist sort of as such in the literature for Landau-Ginzburg models. So let me just make a couple brief comments. Or okay, the first one does, as I contradicted the notes that I wrote myself. There's a weight filtration that's been defined very briefly on twisted cohomology by Sabah. So this is just essentially following your nose with the usual Deligne definition of the weight filtration on cohomology. So this requires that we start with a relative compactification or something resembling a relative compactification of the Landau-Ginzburg model. So your Landau-Ginzburg model isn't necessarily proper. So we choose a partial compactification so that this is proper. And then there's a horizontal divisor with respect to this function, and you can use the usual definition of the weight filtration to define a weight filtration on twisted cohomology this way. This hasn't been studied much. I mean, as I mentioned, this is just a definition that appeared in the paper of Sabah. Secondly, we need to talk about what the perverse Leray filtration might mean, or I guess the more proper thing is we need to talk about what the affinization map looks like. Perverse Leray is clear. So what we expect to be, what we think is correct here is to choose a morphism to AN, some map to an affine variety, so that the restriction of F is proper on fibers of this other function. So we have two different functions here. Y is equipped with a potential function, and you just want properness on those fibers. Okay, so once you have this, you have a class of morphisms or a morphism. So I mean, there could be a bunch of different morphisms that give you this structure, but they should all give you the same filtration. So once you have that, you can use the regular definition of the perverse Leray filtration on the twisted cohomology complex. And you can also use, so this result of Di Cataldo-Migliarini, which tells you that the perverse Leray filtration comes from restriction to hyperplane sections. You can also use that in this specific case. Okay. So once you have that, how can I achieve all of this combinatorially? So I'll make just a couple of comments. So what I want is two different Clarke pairs. I want an initial Clarke pair that consists of just sigma and sigma check as I would have before. Then I want sigma to be included inside of some sigma bar, and my sigma check will stay the same. So I want two different Clarke pairs, and I want one contained inside of the other. The thing that is different here, the thing that I want to emphasize here, and maybe goes back to a comment that I made before that was a little premature, was that I want the support of sigma bar to be precisely the dual of the support of sigma check. Okay, so then what I get is two different things. So the toric variety of T sigma is contained in the toric variety attached to T sigma bar, but the potential functions don't change. These are kept to be the same. And on the other side, the toric variety is the same. Of course, T sigma check is equal to T sigma check, but the potential functions change. So here, W sigma bar is equal to W sigma plus a bunch of monomials corresponding to the extra rays in sigma bar that weren't in sigma. Okay, so the basic lemma here is that the combinatorial setup that I mentioned implies that, first of all, I this here is a relative compactification, or close enough to being a relative compactification that I can compute a weight filtration using Sabah's construction. And the second part, which is sort of mirror to that, is that if I take the corresponding map on the toric on this Landau-Ginzburg model, so the mirror object, perspective mirror object or whatever, the induced map that takes essentially the map coming from all of these monomials, the extra monomials that I added, that gives me something that's proper on fibers. So this basic combinatorial setup of inclusion of Clarke mirror pairs this actually achieves the geometric constraints that I placed in the previous slide. Okay. So once we have that, I think and this is sort of work in progress, the idea is to basically take the inclusion on cellular complexes. So maybe I'll talk about this in terms of the picture because I only have a few minutes left and I don't really need to go through everything. So here's maybe a tropical picture of what I'm saying. So I had sigma check and sigma before, and now I want to include sigma into something sort of like this. So I take some fan where I'm adding rays to sigma to make the support dual, right? So this sort of completes the dual fan or dual cone. So I have an inclusion here. And so on the level of tropicalizations, on this side, what I'm doing is I'm adding this red divisor at the boundary. So that addition will give me a weight filtration. And here, what I'm doing is I'm also adding a potential function there. So what I want on this side is I want to compute kernels of restrictions to this hyperplane. So that's the Di Cataldo-Migliurini definition or sort of restatement of the perverse Leray filtration. It's in terms of restrictions to hyperplanes, whereas the weight filtration comes from this thing that I added here. So, I mean, it's a very rough picture, but you can sort of see just by looking at these things that there's a duality in the picture. The idea is that we have this type of duality. We have inclusions between S and S bar. So we can extend this to filtrations on both sides that should compute the perverse Leray and weight filtrations in these things. Okay, so maybe that's maybe about where I'll stop. Do I have anything else? No, I think that's about it. So I think I'll just leave it there.